We've seen tools for plotting smooth functions and distributions. Let's focus now on actual images. Remember, an image is a matrix of intensity values. That's simple to think of with black and white images with values from 0 through 1, representing black through white with shades of gray in between. RGB color images are stored as three-dimensional arrays, one for each color channel, red, green, and blue. The values are often floating point numbers, between 0 and 1, or integers between 0 and 255. Two of the principal commands in Matplotlib for working with images are imread, which loads images, and imshow, which displays them. Here we load an image sunflower.jpg using imread. The image is loaded into a three-dimensional NumPy array where the trailing dimension, the last to appear in image.shape, is 3. We also use axis off to hide axes when displaying images. To display images, we still need to use the Matplotlib show command to render the image on the screen. This is the default image of the sunflower. There are a number of ways to convert a color image to a grayscale image. A simple one is to average the RGB channels, that is, apply the NumPy mean method along axis 2, the trailing dimension. That is, since the color image consists of three matrices with entries between 0 and 255, using the average works as a reasonable proxy for the RGB values when collapsing them to a single scalar intensity for each pixel. Finding the matrix that is the element-wise average of all three yields a matrix still with entries between 0 and 255. Notice we explicitly set the color map gray so that the subsequent images will all be grayscale. The resulting collapsed array is still two-dimensional and can be plotted as a two-dimensional grayscale image easily. One subtlety regarding the imshow command is pixel shape. Suppose we take the pixels from every fourth row and every second column in the grayscale image. We can do that in NumPy using the slices. Remember that the syntax : 4 refers to every fourth element, and thus our subsampled image, uneven, has dimensions 120 by 320, while the original image was 480 by 640. When plotted using imshow, the image displayed is distorted. The reason for the distortion is that the default assumption is that pixels are squares of equal width and height. When displaying an unevenly subsampled image, the correct assumption here is that the aspect ratio, the ratio of pixel height over the pixel width, is 2. The key word here is aspect. Using aspect equals 2.0 in the call to imshow results in an image with appropriately scaled pixels. Another way to fix this problem is to specify the original image dimensions in the optional keyword argument extent. This can be confusing. The order of arguments for extent is from left to right and from bottom to top. In this case, the optional argument is extent equals tuple 0,640, 0,480. Using the keyword argument extent with an appropriate tuple allows computation of the correct pixel aspect ratio and again, a suitable plot results. Now it's your turn to try some exercises working with images. Let's now extend our toolbox with Seaborn, a library for statistical visualization created by Michael Wascom. Statistics is an essential part of any data scientist toolkit, and visualizing the statistics of your dataset is a valuable way of interpreting and communicating your results. As Seaborn itself states, it provides a high-level interface for drawing attractive statistical graphics. Matplotlib is powerful, but can be complicated. Seaborn is built on top of Matplotlib to make attractive statistical plots with ease. To make the best use of Seaborn, we also need to use Pandas, as Seaborn works best with Pandas data frames. As a reminder, Pandas data frames are tables of data with labeled columns and rows. The columns have shared row labels called an index. The column labels are simply called columns. Individual columns of a data frame are homogeneous in data type and are Pandas series. We'll use a data frame summarizing tips given at a restaurant. It has fields for total bill, tip, sex, age, smoker, day of week, meal of day, and the size of the dining party. Notice the variables total bill and tip are, for all purposes, continuous, while sex, day, and time are categorical variables, sometimes also called factors. That is, they're variables having finitely many possible discrete values. How are the columns of our tips data frame related? One strategy to explore this question is linear regression. That is, fitting a straight line through a scatter plot of points in 2 dimensions. This figure shows a regression line through a scatter plot of the tip versus total bill points from the TIPS data. There's also a narrow band highlighting a 95% confidence interval for this regression. See our statistics curriculum to find out how to interpret this band. To start, we import pandas as PD, matplotlib.pyplot as PLT, and then Seaborn as SNS. These aliases are conventional but not mandatory. They simply make using the namespaces easier. We do want to import pandas because we're working with data frames, and matplotlib because Seaborn needs it. We load the TIPS dataset using the Seaborn load_dataset command. Finally, to plot the points and the regression line with Seaborn, we simply call lmplot, with the columns to use specified as the arguments x and y, and the data frame as the argument data. These arguments are mandatory. Let's look at some other ways to plot with the lmplot command. Remember, our data has factors or groups within data categories. For example, sex is categorized in this dataset as male or female. We sometimes want to compute and plot fits of distinct factors separately. For instance, here are 2 regression fits of tip versus total bill for male and female customers in blue and red respectively. Notice both have a similar slope. Seaborn and lmplot make it easy to color observations and regression curves by factor using, in this case, hue equals sex. The colors come from a color palette to distinguish the lines. We specify the color palette here with palette equals set1. Rather than plotting factors on the same axes with a legend, we may use separate subplots instead, as we see in this figure. Using lmplot with the optional argument col equals sex produces this plot of separate factors. Notice the subplot grid is made without matplotlib's subplot command. Finally, we can plot the residuals, which is how much the data misses the regression line. Notice the dotted horizontal line for 0 residual. The residual plot is constructed with residplot. The calling syntax is like lmplot, but slightly more flexible. X and Y can be NumPy arrays, and the data frame data is not mandatory. We can also have an optional keyword argument like color, consistent with matplotlib. Now you can try out what we've covered in some exercises. This has been a snapshot of Seaborn's regression utilities. Many other things are possible, including higher order polynomial regression or logistic regression. We often want to visualize distributions to better understand our data. We've seen histograms already. We'll now use 3 other tools from Seaborn to visualize univariate, or one variable, data: strip plots, swarm plots, and violin plots. The Seaborn library makes it easy to look at our data even when it can be split into categories. To start, let's look at a strip plot of tip values from the TIPS data frame. A strip plot draws values on a number line to visualize samples of a single random variable. Here, we see a dense line of values clustered between 0 and 5 with some outliers above 5. We also use labeled units on the vertical axis, dollars in this case. Using transparency could show overlap more clearly. In Seaborn, we use strip plot. Given our TIPS data frame, we use the arguments y equals tip and data equals tips for this plot. Remember, Y-label lets us customize the axis label. Of course, the TIPS data is not strictly univariate. It can be grouped into categories, for instance, sex, day, or time. We can also generate a plot grouped by these factors using strip plot with an extra parameter x equals day to clarify the factor column. The code just shown draws this grouped strip plot with parallel vertical strips for each day. We can observe bigger tips on Saturdays, but we still can't distinguish how many big or small tips. That's because on a strip plot, repeated values are drawn on top of each other. To compensate, we can adjust point sizes and add horizontal jitter to spread the points. This way, we can see more tips at, say, $2. The last plot was made with strip plot with arguments size equals 4 and jitter equals true. Here is the same tip data set stratified by day, displayed as a swarm plot. Swarm plots automatically arrange points representing repeated values to avoid overlap and give a sense of the distribution. This makes the cluster at $2 clearer, as well as other trends. The Seaborn command swarm plot made the preceding plot using the arguments x, y, and data, just like strip plot. We can group the data further with another category as a color. The days are already separated into vertical lines. Here, the colors within the swarm plots denote sex. The preceding plot results from using hue equals sex to identify another categorical column. Depending on the number of categories, a horizontal orientation may be preferable. Here, the tips are displayed horizontally with the day categories displayed vertically. To do this, interchange the x and y arguments and use orient equals h in the call to swarm plot. With a lot of data, strip and swarm plots are not ideal. In those instances, box plots and violin plots are more useful. Box plots are illustrations of ranges, the minimum, maximum, and median values of a dataset, along with first and third quartiles and outliers. See our statistics curriculum for a refresher on these terms. Violin plots show curved distributions, notably a kernel density estimate, or KDE, that approximates the histogram wrapped around a box plot, rather than discrete points. The basic idea is that the distribution is denser where the violin plot is thicker. Here's a violin plot of the tip distributions on different days. Violin plot is the Seaborn function that makes this plot. The syntax is simple and consistent with what we have seen so far. Of course, we can combine different distribution plots. Here, we have a swarm plot overlaid on a violin plot. Let's see how we did this. We start by calling violin plot with the option inner equals none to disable the inner box plot. We also choose the color light gray. Next, we make a strip plot with jitter. By default, the strip plot is overlaid on the violin plot. Calling plt.show gives the final plot. We've now seen strip plots and swarm plots for visualizing small to medium-sized datasets, as well as violin plots for inferring univariate distributions from larger datasets. Now you can practice using these tools in Seaborn in the exercises.